Sorry about the delay, everyone.
This is all my part. So let me actually introduce Professor Swarun Kumar. So he is assistant professor at CMU, and I think he was been there for till like
3 years.
From last 3 years. Before that, he got his PhD from MIT, where he was at the base physics at MIT, and even before that, he did his BTech from Madras. He is recipient of lots many awards, including Google faculty awards. So today he's going to talk about city-scale low-power wireless internet, and in general, your interest is in wireless technology, maybe, and also the digital physical layer of the wireless technology. Right?
Yes.
So thank you.
Thank you, Ka. All right. Hello, everyone. Again, apologies for the delay. So I'm going to talk to you today a little bit about my work very broadly on city-scale wireless networks. And so since this is like, more, smaller audience, I want you guys to feel free to just stop me at any point in time, ask any question you want, and let's make this as interactive as possible. So a bit of my my research is basically motivated with this one point, right? Today, in the world over, and of course in India in particular, there's suddenly this large number of people who've been connected to the internet, who have access to mobile phones in a big way, right? And now you can ask, is my job as a wireless researcher done? Because one of the big challenges, one of the big questions that we wanted to do was to connect almost every person to the internet in the world, and this seems to have already, we're almost there, right? What is the next frontier for us tomorrow? And for me, if you ask me, I would say the next frontier for tomorrow is not to just connect every person, but also every object. Everything you buy in the supermarket, you go to the supermarket, you buy groceries, you buy products, you buy appliances, everything will be connected to the internet. And of course, this is not a new vision. This is the vision of the so-called Internet of Things. I'd say city-scale Internet of Things, connecting everything from infrastructure, traffic lights, you name it, parking sensors, speed sensors, your homes, your doorbell, your fan, your light, your refrigerator, your TV, your maybe even your broom and your water bottles, you name it. And vehicles and everything that moves, bicycles. I hear you have like smart bicycles on campus, so they can be connected to the internet, and so that you know if someone stole one, right? So here's the question that my research has been focused on is, what is the quickest and easiest way to connect everything to the internet, right? Every object that you care about. So first, it must be wireless. You don't want to have a wire plugged into your bicycle, right? Or your water bottle or this pointer, for instance. You don't want to charge it every day. I mean, you're okay charging your phone every day. You're not okay charging your coffee mug every day, right? And here's a third constraint that I've sort of artificially added, but it makes sense in hindsight. So you must be able to talk to it for base station like several kilometers or several miles away. And why? Because you don't want to deploy specific infrastructure for each new thing that you want to connect to. So the easiest thing would be is, if I want my smart bicycle to be connected to the internet, connect it to the closest mobile tower. Or if I want my smart glasses or smart ring or smart watch or smart clothes to be connected to the internet, ideally, I don't want to have to go and find out how to connect my clothes to Wi-Fi everywhere I go, right? I just want it to be perpetually connected to the internet. Similarly, if you're going to tomorrow to a supermarket, big bazaar, buying something, you want that product to be connected to the internet from the moment you visited the store to the point you install it to the home. You take that product anywhere in the streets, it should still be connected. That would be an ideal vision. So the only way you can think about it is if this connects to some perpetual city-scale infrastructure, not just something that is in your home. So the moment I list these constraints, it's pretty clear that the traditional wireless technology that we think about, like Wi-Fi, cellular, Bluetooth, none of these have all the three properties, all the three desired properties here. So my research has really been about this. A, what do we build? What is a wireless technology that we can build to connect city infrastructure, right? And objects, everyday objects, to the internet. Yes.
Why does it cellular?
Because you don't have extended multi-year battery life. So when I say multi-year battery life, I mean like 10-year battery life. So ideally, I want I'll explain it more exactly what the constraints are, right? So if you are connecting something bigger and powered to the internet, cellular does do the trick. If you want something that's low power and mobile, cellular is more challenging to be the solution. So one of my research areas has been, hey, how do we develop the infrastructure and the technology? And B, now that assuming that we have such a technology and we have a variety of technologies, not just one, variety for different sorts of power limits, what can we do with that technology? How can we make our life better? What are some of the services that we can run on such a network? So I've done a lot of research on all these different areas at CMU, but I'm going to focus on two of these specific instances in the talk. First is basically this, design of a city-scale low-power wireless network, right? And so here's sort of my vision to make it more crystal clear why it's different from cellular. Let's take everyday object, alarm clock or something, right? I want to attach ideally what's my vision? Attach some very cheap RF interface like a radio chip, and then connected by a 10-year battery. So if you remember before people had smart watches, and a lot of you have these sort of old school watches, right? And they're connected with they're powered by these coin-sized batteries, right? Then you would replace them in almost like 10 years it takes if you want to replace them, or maybe like every 3, 4, 5 years, right? So you ideally want something like that, right? That powers this chip, and this whole system should be able to talk to a cell tower that is several kilometers, several miles away, right? Can we get such a system up and running, right? And you don't want to send a lot of data because you don't want way too much data from your alarm clock. You're not watching a YouTube video or Netflix or something on this. You're just sending a few bits of data or a few bytes of data. So is this real, right? So if you, so actually this falls under a broader umbrella of something called low power wide area networking technology. There are lots of these new age chips, like companies like Sigfox, companies like LoRa, standardization bodies, 5G standardization technologies, like 3GPPs, narrowband IoT, and all of these systems try to do something like this. Their plan is to do something like this, right? Basically, think of it as take a cellular chip, cut away all the unnecessary and unwanted interfaces, make it as thin and as lightweight as possible, connect a 10-year battery to it and see if it works, right? Assuming you're sending a very small amount of data, right? But even if you do such a thing, would you actually get the 10-year battery life? Would you actually get the long-range performance? So we actually, in Pittsburgh, built this infrastructure where we built like 4 outdoor gateways, many indoor gateways spanning like a large neighborhood. And we wanted to measure how much of the entire city can we cover with infrastructure set up on the CMU campus and in surrounding neighborhoods. And so the coverage, even though we sort of like a 10-mile radius that was promised, our coverage is actually the signal is much weaker, right? We actually only see a few kilometers of relatively reasonable coverage, and the coverage really drops off pretty badly everywhere else. And here's the other interesting problem that we observe. The coverage is not uniform at all. And this is like a standard problem in wireless, even more when you have low power wireless. So even if you have your tower right in the rooftop of this building, if you go to the basement, you're going to get virtually no signal, very significantly weaker signal. So while these technologies, if you think about it, they're not completely new. So imagine like wildlife tracking, like National Geographic, you see these tigers move around with chips and trackers, right? They're not, believe me, nobody's charging a tiger every day, right? They're somehow being connected to some radio tower to get data on, is the tiger alive? How many tigers are in this national park, right? Now the challenge there, the advantage there is it's open area. It's more like a relatively unpopulated space, savannas and so on, right? But the moment you bring these sorts of technologies to cities, to a city like Bangalore, to a city like Pittsburgh with lots of tall buildings and lots of an urban landscape, uneven surface, your network performance is significantly poor. So you need to have new technologies to circumvent this. So what does this sort of coverage unevenness mean in terms of battery life? So the biggest contribution to battery life, the biggest drain on battery life, it turns out, is the transmit chain. It's a radio transmitter. The device sleeps, when the device sleeps, the power consumption is much lower. So what this means is that if we can somehow reduce the power, right, that the device transmits over a long duration, we can significantly save battery life, at least for these classes of devices. And that is even more important and challenging in the context where coverage is very poor. So you have to transmit, if you're in the basement, you have to transmit even higher power just to be heard. Right? So in this context, we sort of have this insight, which is with these base stations earlier, of the long shot of 10 years ago, and even like a few years ago, used to be that you have a cell tower, and a big cell tower on a hilltop, on a rooftop, covering multiple kilometers of users. But that's not how cellular networks future cellular networks are evolving. You might be surprised that you walk down, you might find a geo cell tower attached to like a lamppost on the street, right? Cell towers are getting even more and more prevalent. They're getting smaller, they're having smaller coverage areas. But another trend that's happening is that cell towers are being installed in your homes. Future set-top boxes, like for example, Comcast in the US, is planning to install like these sort of low-power wide identification chips in their set-top boxes. So suddenly, it's not just that you have cell towers on the rooftops that cover a larger area. You also have a large number of these mini or femto base stations, as they are called more formally, towers that are propping up all over in a more distributed network, right? So can we use this prevalence of a large number of cell towers, maybe not as powerful, to extend the battery life of the devices, which is ultimately the currency that we want to improve, right? And so this was the insight behind our system, which was called Charm and IPSN, which basically is a system that tries to extend the battery life by using the multiplicity of gateways, or basically base stations around us. And the key idea is like very, very simple. Let me ask you a question. So if you have a phone, right, your phone connects to a tower. It connects to a cell tower, right? And now if you walk, you're here, you go to downtown Bangalore, you go to MG Road, it connects to a cell tower in MG Road. Here it connects to a cell tower in IISc. Why? Why should you be connected to one cell tower at a time? Why can't you be connected to many cell towers all at once? Why did we even constrain ourselves in a mechanism to connect a device to one single tower, right? Because in principle, wireless signals are broadcast. If I transmit an audio signal here, everyone in this room hears. Probably some people in the neighboring room may also hear what I'm talking, right? So in principle, if a cellular device, if any device, right, is talking in IISc, there's some weaker component of the signal that's being received by all neighboring towers around IISc, right? And particularly if you now have set-top boxes, if you have more of these base stations set up all over the city, you're now create not all equal strength, some weaker, some stronger signals received in multiple different towers. Now, instead of dedicating one of these to be the decoder, why can't we essentially listen to all of these signals? So basically take all of these signals, combine them at the cloud, and then try and infer the underlying signal transmitted by the device. So it's a very simple concept. So essentially take the signals from this transmitted device across all the different towers and then add them up. Now, if you did physics, if you studied physics 101, you know that if I have a bunch of signals, I can combine them constructively or destructively. I can combine them to reinforce or cancel. So take these signals, combine them, figure them out how to combine them constructively, reinforce each other, and you get a much stronger signal, coherent combining. Right? And this signal is going to be much stronger, which means your device can transmit at a lower transmit power to get the same quality of service. Right? In a sense, at the same distance, it can consume less battery life. Now, this is a very, very simple principle, right? Why didn't people do this in cellular? Why is this so challenging? The main challenge is the backhaul, right? If I'm not just sending the data, if I'm sending raw received signals from each tower, everywhere, all over the city, you're suddenly going to have an explosion of data sent on the uplink, right? Now you might say, hey, why don't we just send all signals upstream and at least chop out the portions that contain packets, right? At least that will make it more efficient. Here's the problem in the low power context. Your signals are super weak by definition. What does super weak mean? They are well below the noise, right? I can't even see them. I'll just see garbage signals unless I have enough power for the signal to pop up above the noise, right? Which means that for all practical purposes, you have to send all the signals that you receive upstream, combine them at the cloud, and only then you will see some signal above the noise. And this is something you certainly cannot do, right? So to address this problem, let me show you a very specific example of one technology called LoRa, which is what our system is demonstrated on. So the idea behind LoRa is something like this. If you don't understand anything, it's very simple. You send either a 0 or a 1 in one of two patterns. You send a 0 like this. Basically, it's a frequency sweeping of a signal. The signal's frequency increases as a function of time. So you send a 0 like this, you send a 1 like this, for instance. If you want to send a very simple sequence of signals, you send a very simple sequence of zeros and ones in this manner. So what you typically do when you want to detect a packet is there's a signal. The signal has a very specific pattern, right? And it always starts with something called a preamble. A preamble is an initial part of the packet that indicates that, hey, this packet exists. So you take this preamble, you match it against another sequence, right? Which is called a known preamble, right? The initial part. So everything starts with a very specific initial pattern. This is true for Wi-Fi, it's true for cellular, it's true for any technology, right? And then you match it, and if you see a spike, you know that the signal exists, and you can proceed. If there's enough signal above a threshold, you know the packet actually exists. But here's the problem. If you're just using a preamble to detect a packet, the signal is too weak, right? This preamble's matching will never hit above the threshold. So what we do is a very simple idea, something called enhanced detection. And the idea is this. If you look at the preamble and the data are not, now notice that our earlier approach only uses the preamble, it only uses the initial part. We throw away the data. We don't care what data the device sends, right? We're only looking for the preamble. But notice that the data is not arbitrary, right? Remember the data, what was the data? It's a series of chirps. It's a series of patterns. Some of them are like this pattern, some of them are like this pattern. There's a pattern to it, right? They're both shifted versions of each other, right? They're both shifted versions of each other. What this means that if I somehow take this earlier picture and fold it, draw them out on a piece of paper and fold it, right? This looks like a much more uniform pattern. It doesn't matter what the data is, what the 0 and the 1 is. The 0 and 1 are simply shifted versions of each other. So if I take a paper and fold it in between, suddenly this pattern looks exactly like a constant stream, regardless of whether there are zeros or ones. So what this means is, I essentially have converted my data into a preamble, into a known pattern that I can now match to find the energy. Is this clear to everyone? Right. So we essentially use the entire packet, and as a result, we can detect signals that are significantly below the noise, even at a single base station. Yes. Sure.
So the preamble is supposed to tell the receiving station, okay, look, here's expect to receive data.
Yes.
Data followed, right?
Yes.
Where is that preparatory stage here? Is that sort of lost?
So here's the idea. We don't have these two as separate stages, right? Typically, what do you do? If you're sending a message to me, you initially say, hey, I'm going to send a message, and I'm going to have a specific pattern in the beginning to indicate, regardless of what you send. It's like an identity or a technology specific pattern. Every Wi-Fi radio, for example, your phone, if it's transmitting a message, it transmits a particular sequence, an initial sequence, just for detection. Then it sends its data, which can be any combination of zeros and ones. We say, if you use just the preamble alone, the signal is too weak to detect because it's a very low, small battery powered devices. The data is composed of zeros and ones, but these zeros and ones are not random sequences of random signals of zeros and ones, they have a pattern. The 0 and the 1 are transforms of each other in some way. So let's not just use the preamble to detect the packet. Let's use the preamble and also look for the way the zeros and ones are encoded. And in combination, that will give us much more enhanced, much more powerful detection. Does that make sense?
I'm still not clear about the design of data.
Okay. Data is variable. So the data is, you're saying the length of the data is variable? Yes. Yes. So what we do is, the key idea about this is to fold this variable sequence into a consistent sequence. Yes, if I know how the zeros and ones are encoded, I don't need to know whether it's 0, 1, 1, 0, 0, 0 or 1, 1, 0, 0, 0. I don't need to know the order of the zeros and ones. But as long as I know how zeros, what a 0 looks like, what a 1 looks like, if I can somehow make a mapping that keeps the zeros the same and transforms the ones into the zeros, then I'll always get zeros. So we look for those, we essentially transform the encodings into a uniform sequence that we can then detect. That is a very simple idea behind the system, right? And then we can perform detection of the sequence. So we are only detecting. Once you detect, we still haven't decoded it yet. So at this point, we know that there is a packet, and we know there's a packet even if there's one base station, right? That gets the signal. So let's see how we decode next, right? So the advantage of this is that at one base station, you can now very quickly detect some weak signals, and then you get a huge amount of bandwidth saving. You can send these signals upstream, up to the cloud, and you can upload samples only when you detect, which saves bandwidth, right? But the second thing is, remember that it's not enough to get this one sequence. One base station is not going to give you the data. You need data from across multiple base stations, right? Now, if you need data from across multiple base stations, it's not enough to know that you got the data. You need to know, that it's the same packet that you've received across multiple base stations. So if you got this data sequence at 5 seconds, you need to know that the data you received at the other base station is also the data from exactly t equals 5 seconds. Right? So we need accurate time synchronization across base stations, and you need to fetch the information concurrently. So we have a bunch of strategies. I'm not going to go into the details for this talk. One is a two-step process. First, we use these GPS synchronized, highly synchronized clocks to get a few milliseconds of time synchronization. Then we have another process called phase-based synchronization, where we look at the structure again of these sequences, signal sequences, to know up to a sample, which is up to of the order of microseconds, exactly how these two transmissions look like, right? And one of the advantages we have in this system is that it's remember that I said your cell phone, it's not like your cell phone, it's not like YouTube video, it's not sending a lot of data. So we have very, very weak deadlines in terms of how quickly we need to respond to acknowledgements, how long the packets are. And so that's a significant advantage in that we don't need to be as tightly synchronized as cellular is. So now that we have the signals from across multiple base stations, here's a question. We did this trick. We are able to enhance the signal detection at one base station, at some base stations. At the cloud, once we have the copies, time synchronized copies from across devices, we can add them constructively. But you might wonder, this requires me to detect this packet, this weak packet, at a large number of base stations. What if I miss it? What if I miss it at some base stations? Right? And the idea is to solve this, it's not, you don't need to quite detect the signal at all base stations. All you need to do is to detect it at one base station. Why? So if your signal is received at multiple different base stations, let's say one of them is strong, the other two are weak, right? So you get a strong copy here, you get these two weak copies. In the stronger copy, you detected with enhanced detection the packet. These two guys, you missed it. You thought it was garbage. But what we say is, if you get a signal that looks like garbage, don't immediately throw it. Store it for some time. Have a circular buffer, store it for some time. Now this guy will realize it's a packet and he'll send it to the cloud. The cloud will validate the process just to make sure that there is actually some energy that looks like a packet. And what it'll do is it'll prefetch the packet from neighboring base stations, even if they're supposedly garbage. Then it'll take these, add them up constructively, figure out that there's a packet and decode. So all you need is at least one base station should figure out that there is something that looks like a packet. And then at the cloud, you can do the coherent combining, get the signal above the noise. You can do decoding as you would normally do and get the zeros and ones. Right? Yes. Yes. Oh, H1, H2, Hn represent the transformation, the signal transformation. The same signal is being sent, it's just that they are some of them is stronger. H1 might be a bigger number. That we will do here at the cloud. So we have these three packets, we'll combine them constructively at the cloud. We'll add. If you do it on this, so our whole principle is very simple. There is an inequality here, right? There is non-uniformity in terms of capabilities. This device is an extremely low power device. These are more capable, not infinitely powered, but more capable base stations. The cloud has a lot of computational capabilities, at least in this context, right? You're not sending huge gigabytes of information. You're only sending a few bits per device, right? So what we're doing essentially is the strategy so far, the approach so far has been, let's create better modulations, better devices that can transmit signals more accurately, that can transmit that can be more battery efficient and so on. We're saying these guys are already energy starved. Don't try and hurt them more, right? The infrastructure is much more capable. So why don't we build better infrastructure, more powerful infrastructure to outsource, the challenges of detection, decoding, and so on. Let's push it to the cloud. Right? And here it actually makes sense because pushing it to the cloud means you get more battery efficient devices at the end of the day. That's essentially our working principle.
One of the requirements definitely is that the RX2 to RX1 to RX10 change completely time sequence, right?
Yes.
Down the speed, speed and doubling actually creates problem because now, on the cloud, what you will get back is that seems like I want you give me the signal that you received at this point of time.
Correct.
Right? Now, if it clocks a little bit off, you get something else.
So we have two strategies to deal with that. So first is we have GPS synchronized clocks that you see some millisecond synchronization, right? Second, we do a phase correlation. So we have this, we do a phase comparison and which gives you sample level synchronization. That in itself should be enough. On top of this, remember that these packets themselves are very slow, sending at kilobits per second, as I said, right? Which in the packets themselves last for like tens of milliseconds, much longer than Wi-Fi. A Wi-Fi packet lasts less than a millisecond typically, right? Which means that even if you have some buffer, if you just provide packets to within some buffer on the left and the right, you'll most likely, the packet will exist somewhere in there, right? And on the cloud, you can then do the enhanced detection to try and figure out exactly where the packet is. So all these, there are lots of time synchronization. There's an entire, couple of 3 pages on time synchronization that I'm sort of compressing into one slide here. But that's basically what goes on in the system. It's right. Time synchronization is very important. It's something that we have to rely on. Otherwise, the system will break. Okay. So we actually built this out. So this is our custom built gateway with an FPGA and front end antennas. We essentially receive and process raw IQ samples like an SDR, and this interfaces with a Raspberry Pi embedded platform, so we can have very compact base stations. And you can also attach it as auxiliary hardware to existing cellular gateways if you choose to. Right? So this is what a full hardcore cellular gateway would look like with weatherization and so on. So we actually went and deployed this, as I said in one of your earlier pictures. We had 4 to 5 gateways, different parts of our campus as well as Pittsburgh, Oakland area of Pittsburgh. And so this is our system accuracy, essentially showing that we get a much better packet detection accuracy with enhanced detection compared to just pure local detection compared to what LoRa typically does. So we get significantly higher performance. The x-axis is in dB, decibels, which is in log scale. So we're getting significant advantages in how accurately we're able to detect the packet, including at very, very low signal quality. And what does this mean in terms of battery savings is quite significant. So I'm going to focus mainly on this graph. You see that in principle, the amount of battery life that you can get with more gateways. One gateway, you get maybe, depending on how many messages you send, maybe 1 to 2.5 years of battery life. With as few as 4 or 5 gateways, you can get up to 10 years. And beyond that, we don't get gain because the battery runs out regardless after a point. And so just having 4 or 5 gateways and being able to constructively combine signals can give you very significant performance benefits. Right? So any questions so far about charm in particular? Yes. Y-axis is years of battery life. So we didn't actually, so you might ask, did we actually run this experiment for 10 years? I don't have a PhD student who took 10 years, who did this experiment for 10 years. So we looked at a simulation train for a 2-month period. We fitted it into battery, well-known energy battery models, and we extrapolated on what the battery drain would look like for longer duration. That's the only way I can graduate students. Right? So going back to sort of this vision of attaching a battery to radio and the cloud, I want to give you a little bit of a flavor of something else which is more recent. Can I get rid of this battery? Right? Is a question that we also wanted to ask. Right? Now, here's the unfortunate answer, no. Right? Because if you want several miles away and you have to transmit within like power limits set by the FCC or DOT in India, right? And you don't want to roast humans, basically, right? By sending too much power, you can't get this distance because there's something called Shannon capacity theorem in information theory. If you know about it, it says that there's an upper bound on how much data you can send with a given signal quality ratio and limited bandwidth and so on, right? So that's information theoretically or physically, if you want, mathematically impossible to get this range. But maybe right now, it is possible to get like 5 to 10 meters. And where have you seen this sort of a technology that attaches something and you get 5 to 10 meters of range? So this is something called RFID technology, right? It's like there in your ID cards in some where you scan and tap, or in the US, for example, there are toll readers, toll systems where your car goes and you automatically get billed a toll, which is also based on RFIDs. If you go to a shop and you shoplift something, which I don't recommend, right? There will be a beeper and buzzer that alarm that sounds, right? That's also based on RFID technology. Books, if you borrow books from the library, many books also have RFID for the same reason, to track, to know which book has been scanned. And again, if you take the book out of the library, you will get into trouble and things like that, right? So this has been done. And the 5 to 10 meters is more than enough. Actually, operating distance of many systems even smaller. They usually have like this sort of archway or a reader of some sort, and if you go out of it, you get caught, right? Theft detection systems, right? And there's no battery attached to these, right? Because you want to make it very simple. The cost of a RFID is like few cents, right? So it's like few paisa in Indian rupees, right? It's like literally like 10 paisa or something to get one, right? So, but can we do better? We're not at 5 to 10 meters. Can we do this better? Like, I'm not thinking like kilometer, but maybe like 50 meters, right? Can you do like 10 times, 50 to 100 meters, say, right? So this is what an RFID tag looks like, as I said, right? And how does an RFID tag work? And why does it not require a battery? 101. There's a reader. Reader transmits a signal, right? Tag is not a transmitter. Okay? Transmission needs power, right? What the tag says is a reflector. It's like bounces, right? And it's a specific kind of reflector. It's a reflector that you can turn on or off. It's an electric reflector, if you will. So if the reflector is on, you get a signal back. If the reflector is off, you don't get much signal back, right? And so depending on whether the reflector is on or off, you get a series of zeros and ones, which can be identity, which can be some sensor attached to it, sending data. It could be anything, right? That's how a RFID tag works. Typically, it's like just an ID, right? So if I get an alarm, I know which thing you shoplifted, or if you scan your ID card, I know who you are, and therefore I can grant access or not grant access. That's typically what's done, right? So the max range you can get to the high state-of-the-art RFID like 10 to 15 meters. Can we do better? Can we push the limit of this, right? And so this is a very, very recent hot of the press work, right? A system called Push ID, which pushes the range limits of RFID tags to like 60 meters, right? So how do we do it? Again, there's an analogy with Shan. The idea is, so imagine you're in a store. You have multiple entrances. You have multiple RFID readers at the gateways. Imagine you're in a factory floor. And this is perhaps one of the biggest consumers of RFID tags, product inventory tracking. So if you go to any manufacturing plant and you have individual pieces of products that are manufactured, they're all tracked, typically with barcodes, but more recently with RFIDs. And there are RFID tag readers that track them at every single gateway point to make sure that the correct product is being assembled and counted, right? In any workflow, any faculty workflow. Now, instead of individual tags being scanned at these specific checkpoints, like exits, like stages inside a factory, like inside just the checkpoint of the library and so on, can we use all these RFID readers collaboratively to improve the range, right? Just like we use a similar idea for Chan. The question is basically, can we essentially use these multiple readers to beamform energy to an RFID tag, and therefore we can improve the range. So a lot of our theory here is similar in terms of being power. So I wanted to focus on the key difference with RFID tags for you. And very simple point, there's a chicken or egg problem, right? Now remember that in the low power case, I got a signal. It was a very weak signal, but there are these local enhanced detection tricks that I could do to get the signal, time synchronize, get these pieces. So once I have the pieces of the signal, I know I know how to add them up constructively. Right? I know how to add them up constructively. But with RFID tags, an RFID tag is not going to respond unless it has enough energy to respond. Correct? Because doesn't have a battery. Right? I have to beam power to it, and only then it will respond to me. Correct? So if I want to beamform, I need to know exactly which direction. Okay, I don't know if there's some beamforming going on here. Like I'll widen my arms. If if I want to beamform, I need to know exactly which direction my device is, right? Some approximate location, if you will, to know how to, send my power in that direction, right? But to know where you are, you have to first send me a beacon, right? Only if you send me a beacon, I can guess where you are. Now there's a chicken or egg problem. I don't know where you are, right? And to know where you are, I need to transmit power to you so that you respond and tell me where you are. Like chicken or egg, right? And so this is a dilemma. So the way to deal with this, I'm going to be a very high level approach. I'm not going to go to the details here because I want to move to the next module, is we actually model the way the signal transmits power. So if you had an array of multiple antennas, can you explore the space better? Can you essentially figure out which direction to transmit power efficiently so that you cover the entire space with the least number of beams? Well, this is a relatively easy problem if you had like antennas in a very nice geometry like this, because beams are just angles. So you can say, I have a lighthouse. How do I illuminate the entire sea? I phase it in all these different directions. Hopefully I illuminate the entire sea, find all the ships, right? Or that's an analogy, right? It's more complicated if you have antennas all over in a distributed fashion. If you have antennas all over, you don't get these nice beams of power. You get these weird patterns of constructive and destructive interference. Remember that? Like the signals from all these different transmitters are going to collide. They're going to create points of constructive interference. You're going to create a lot of non-uniform points of destructive interference. So we actually, a lot of where the details of the paper, I'm not going to go into it, is figure out how to adjust these powers, adjust these phases, so that we cover the entire space, even though there's this weird constructive and destructive interference going on. Just to provide a context of how difficult this is, if I attach a wall here, if I add a wall, this pattern changes, even if I didn't do anything to the setup, right? How the signals constructively and destructively interfere. So I need to have a very good grip of what's going on in the network for me to detect and scan all the tags very quickly. This is really what the core contribution of the system is all about. The result of this was that we were able to get very significant accuracy, distance. So you remember that state-of-the-art systems for RFID tapers are around 10, 15 meters. For the same exact model of tag, we didn't modify the tag. We didn't even modify the reader. We just took the signals to the cloud and we did a clever configuration of it, right? We got significantly higher distances, like 60 to 70 meters maybe, depending on the context, whether you line of sight, non-line of sight, the blockages and so on. All right. So now that I talked a little bit about various ways of designing and transmitting power to RFID tags to whether you had a battery or not, right? What can we do with it? Like what are some of the interesting applications we can build in this context? I'm going to talk about one very simple instance, which is wireless shape sensing. So here's the idea, right? We have these RFID tags in our previous example. Can we deploy them and sense what's going on in the world, right? We want to create a shape responsive world. So the idea is that we just took a bunch of RFID tags, attached them to surfaces, and we want to model how they change in shape, how they change in curvature, and so on and so forth. So the idea is you have toys, you can bend and you can understand how they deform. You have carpets, you know exactly where people are stepping on. You can also build this in scale, have an entire bridge and see how it's interacting with stress and so on, right? So if you look at how people have typically monitored the shape of something, they have essentially something like external infrastructure. They are deploying cameras or they're deploying high-end solutions that go around and scan the surface. So if you look at how 3D movies are made, like Avatar, like those sort of movies, right? Like 2.0, right? They basically have a bunch of, tags, infrared tags attached to Rajnikant, and he moves around and then they animate the robot. Right? So so another approach of doing this, of course, the challenge with that is you need to have a camera pointing at you. You need to have a camera pointing at the surface all the time, which might not work, particularly if you're moving. If you're moving around and you want your shape to be tracked. Another approach is to build dedicated smart materials that can sense the shape. Like this is something called sensor tape, but of course it's more bulky, more brittle, often requires a battery. It's not washable, right? So attaching it to fabric. So ideally, what we want is something that is, that works in non-line of sight, that doesn't require you to actually directly have a view of what the shape is, and you want it to be battery free. And so this is what we did, which is like a shape sensing solution where the user touches different parts of the surface, and you see in the bottom right, I don't think you see it very clearly animated. You see the shape being found of the system, right? Sorry, these are out of sync, right? So the idea of the system is quite simple, right? Basically, if you have a tape with RFID tags attached, can you essentially find out how the curve of the RFID tags look like, right? And specifically what we do is we sort of flip how typically RFID tags and readers operate. I told you earlier, you have these checkpoints, you scan the RFIDs as you walk through. Instead, what we say is that people have RFID readers in their pocket, right? If you think about it, NFC, which is sort of like a short-range version of RFID technology, is already there in many smartphones. So it's not unimaginable to think that future smartphones will have RFID technology. So can you use the phone in your pocket to detect the shape of surfaces around you, including your clothes, including the surfaces? So the idea is, again, I told you how RFIDs work. They work on these signal reflections. But what happens behind the scenes is that they introduce a phase change. Right? When a signal transmits from the reader to the tag and the signal bounces back from the tag to the reader, you get a slight shifted version of the transmitted and the received signal. And this shift depends on the wavelengths, depends on the distance between the transmitter and the receiver. So your wave that is reflected back from the tag is not going to be exactly in phase with the signal of the reader. So to put this in perspective, if you had 1 degree of phase shift, that's pretty accurate. You get 0.1 millimeters of shift in the location of the tag, right? So that's essentially what we do. So what our system does is it reconstructs the shape of the RFIDs, of the RFID curve based on these various observations. Because there are many challenges in this. you have this problem of too many variables and too few equations. Basically, remember, assume you have RFID tags all over my t-shirt, and I want to tag exactly how the shape of my body moves as I curve, as my spine curves, and so on. Right? I only have one antenna, so I only get one signal per tag, but I don't know the location of exactly where these tags are. I don't know the multipath. If there is some wall that reflects a signal, I don't know that. Right? So it feels like there are too many variables and too few equations. Right? So our key idea is very simple. Right? Even though it feels like there are too many variables, it's not completely arbitrary. Right? Even though my body curves, my body is not curving in some arbitrary shape. There's some sparse parameters. There is a few parameters that dictate the curvature of my body. Right? Similarly, even though there's reflectors in the environment, I'm not affected by all reflectors. I'm only affected by a few major reflectors in the environment. So you can use these insights these sparsity insights to reduce the number of variables quite significantly and still solve the system. Right? So one thing we do is we model these sort of surfaces of the body using something called parametric Bezier curves, which are basically from graphics, right? That model the shape of like different curves using a few control points, right? So we fit, I'm not going to go into too many details because of time. We essentially say that the key idea behind this is you can take any curve. If you did curve plotting in Microsoft Paint, for example, right, or PowerPoint, what do? You specify a set of control points, and then the curve automatically retrofits around, right? Basically, you're specifying a lot of points on the curve using a few series of control points. So we use a similar principle. Your body's curvature can be modeled with a few control points, not the location of each individual RFID tag on the body, right? So there's a bunch of curve modeling literature that I'm just going to skip, but basically, we essentially solve this problem by modeling these curves. But now that you have the curve, you have an infinite possibility of curves. Right? Even if I set key control points, it's not just one control point, right? Even if there are 4 control points, the 4 control points could be in infinite locations. So it's not like you've reduced the number of parameters, and you still have an infinite search space. So to reduce this, we developed something called a genetic algorithm, and this is used in many different communities with machine learning. Broadly, the idea is let's model this as like how Darwin would, right? Let's essentially say create a DNA. A DNA is basically something, an individual. An individual here could be a curve, some parameters for a curve, right? Let's have an initial family of curves who existed in the world, right? Let them battle it out and then do natural selection, right? Natural selection is some curves live and some curves die, depending on how well they actually fit the observed wireless channel measurements. And based on these measurements, we then find the next generation by, crossing over the successful curves from the previous generation and eliminating the curves who died, right? And we repeat this process over and over again until we find a successful family of curves. It's a very elegant optimization problem for these non-convex sorts of problems. So now that you have it, you can model curves. How do you model surfaces? Bezier surfaces instead of Bezier curves. I will leave it at that, and you can see the details in the Mobius paper. So how did we evaluate this? We actually put this on fabric, we put this on cushions, we put this on like tapes and so on and so forth to actually measure. These are RFID tags that you see on all these different surfaces. We actually had camera systems as a fiducial marker for getting the ground truth of the system. And overall, you can see very high accuracy. Note that the x-axis, the y-axis here is in centimeters. So we are getting a very, very minute sort of error between 1.3 and 1.9 centimeters over meters of distance. This is all showing you an example of how the predicted shape and the ground truth shape looks. So there's a lot of overlap in the predicted and the observed shape, right? And we can actually do pretty well. We just get maybe like 2 centimeters of error instead of 1 centimeter error when we have multipath, like reflectors and non-line of sight settings, right? And we actually do lots of stress tests. We do stretch, we do bend, we do all sorts of funny materials like rubber and things which are like much more difficult to where our assumptions fail, and you can see all those details in the paper. I think one of the most interesting things we did is we took all these Rfid tags, put it on a bridge, sort of combining all the different papers, long range, low power, and then sensing, right? So this is so Pittsburgh is known as the city of bridges. If you ever visit, they have a large number of bridges, right? We have like, I think 200, 300 bridges, because we have like 3 rivers. This is one of the bridges, actually one of the smaller bridges. We attach a bunch of RFID tags on them. And basically we found that the shape that we got is very, very closely aligned with a very recent survey that they had done on the bridge itself. And so we can do very, very large scale mapping of infrastructure using like dirt cheap components, like sense, right? So a little bit of glimpse into future direction just to wind up. So I'm working on this very large collaborative projects called Open Pittsburgh Wide Low Power Network. We have a bunch of software radio base stations from my lab. We have rooftop base stations with another lab called the Vice Lab, and we have this sort of traffic, the bumps, the stickers like that you hit when you drive. There are like these bumpers, they're called traffic dots that you hit. So we instrumented LP1 radios into those in collaboration with Professor Bob Iannucci in Silicon Valley. And now we have this sort of large scale network operational right now in Pittsburgh. And we want to do a lot of interesting things with this network. We want to take all the data, the raw signal samples, the sensed data that we get, all the measurements that we get in terms of location and timing, take them to the cloud. We can develop new communication protocols, there's new networking protocols. We can do interesting services like location tracking. Hey, where is the smart bike, for example, right? And we can also do sensing, like can we know if there's an earthquake? Can we know and the bridge shakes? Can we know if it's snowing and in which parts of the cities it's snowing? Can we make those sorts of measurements at wide scale and really do city scale shape sensing and infrastructure sensing, not just of individual devices, right? So we're actually a very large team of researchers, 15 researchers who are working on this interdisciplinary project. So it's not just me. So let me just summarize by saying that we are sort of at this arc. We connected like almost like the world population, almost to the internet as of 2019 actually. And we are already at this cusp of this Internet of Things where a large number, billions more will be connected. 5 billion are connected, there's 50 billion to go, right? And so I showed you 2 examples, but the broader theme is that we need to find new ways to connect these devices, and also use the information that we have so that both connectivity and sensing can simply disappear from our life, services that we can just take for granted. And with that, I'll answer any questions you have. Thank you.